Hello, and welcome to my talk for stochastic light culling for single scattering in participating media. My name is Shin, and I'm a graphics engineer at AMD. Volume rendering is essential to add realism to rendered images. Examples of volume effects are light shafts and fog effect like this image. Also, volume scattering on primary layers is more visible compared to volume scattering on deeper passes. In the literature, tree-based light sampling technique is often used when rendering a scene with many light sources. Because of the nature, we need to maintain a hierarchical data structure for light sampling, which could be a burden sometimes, especially for real-time applications. Then, a question we had when we started this research was, is there a lightweight light sampling technique which we can use if we apply volume scattering only on primary layers? It should work without a hierarchical data structure. An obvious choice here would be light culling. Especially, type-based culling method is used for many real-time applications. In this method, lights are beamed into 2D screen space tiles, considering the limited light range, which can be achieved by light culling. It is good as we can cull lights to reduce the computational cost. However, it's not suitable as it introduces a noticeable darkening bias. On the other hand, stochastic light culling is a good fit for this purpose, because it does not make the rendering image darker, while we can still cull light sources. In this method, the stochastic follow function can be approximated using a Russian roulette technique by randomly sampling the fall-off function with a proper probability. Considering this stochastic fall-off function, we can define the random light range for each light source. As this figure shows, if the shading point is inside the limited light range, we accept its right for shading. On the other hand, if the shading point is outside the light range, then we can reject its right before shading. However, this stochastic light culling method is originally proposed for surface illumination. Then, in this work, we extend it to volume rendering. Because the stochastic follow function is discontinuous, we can define two bounding spheres based on Russian roulette. We newly introduced the inner sphere here, which represents 100% acceptance range, while the outer sphere represents the stochastic acceptance range. Between inner and outer spheres, stochastic follow function is constant as this figure shows. Comparing to the application to surface illumination, the situation is slightly different when we use it for volume, because now we have a ray segment instead of a single shading point. Therefore, for these two bounding spheres, we need to do a ray-sphere intersection. But then, how does the ray intersect with these spheres? Here in this paper, we consider these three situations. Case A, the ray doesn't intersect with the outer sphere. Case B, the ray intersects with the outer sphere, but not with the inner sphere. Case C, the ray intersects with both spheres. Then, let's consider these three cases. First of all, let's choose case A, not intersect with the outer sphere. In this case, we can simply reject and cull its light before shading. So, we don't need to consider its light. That's it for this case. And the next is the case B. Intersect with the outer sphere but not with the inner sphere. In this case, the stochastic follow function is constant in this range between the inner and the outer spheres. So, we can sample the shading location uniformly between these 2 points, T0 and T1, with a constant PDF. And finally, the case Shin, intersect with both spheres. This is the most complicated case to compute. In this case, in order to decide the sample location on the ray, we need to consider 3 segments, between T0 and T1, between T1 and T2, and between T2 and T3. On the segment T0-T1 and T2-T3, highlighted with blue in this figure, PDF is uniform because the follow function is cancelled out with the Russian roulette probability. And on the segment T1-T2, highlighted with orange, PDF is proportional to the follow function. Then, we can define how to sample the shading position for each segment, considering each PDF. On the segments T0-T1 and T2-T3, we do uniform sampling to sample the shading location with a constant PDF. And on the segment T1-T2, we do equiangular sampling between T1 and T2, with a PDF proportional to the follow function. If you want to know more detailed explanation, you can find it in our paper. Now, we can efficiently sample the shading point for all these 3 cases. However, so far, we assume the lights are point or sphere lights. Then, the question is, can we apply this method to area lights? I will explain it from now on. Our method is applicable to arbitrary shapes of area lights by generating VPLs on the area light surface. Simply thinking, we can consider bounding spheres centered at the VPL position, similar to the point light case. However, the radiant intensity of VPLs depends on the area light normal. The ice surface of the radiance emitted from the VPL is shown as a blue shape in this figure, which is derived from the existing paper. So, considering the bounding sphere centered at the VPL, most areas inside it are not necessary. Therefore, we can use tighter bounds for VPLs for simplicity here. But it's not that easy to consider the intersection between the ray and this shape of the ice surface. So, in this paper, we use the bounding sphere for this ice surface, which is shown as an orange sphere in this figure. Considering these tighter bounds, we can handle area lights more efficiently. With this bounding sphere, we can also define 2 bounds for area lights like the point light case. And with these 2 bounding spheres, we can handle area lights in a similar way to point lights, considering the same 3 cases. Again, in each figure, the blue sphere shows the outer bound, which represents the stochastic acceptance range, and the orange sphere shows the inner bound, which represents the 100% acceptance range. Then now, let's move on to the results of our method. But before showing the results, let me describe our implementation a bit. We benchmarked our method using tile-based light culling with a tile size of 16 by 16 on the GPU. All experiments in this paper were executed on an AMD Radeon RX 6900 XT GPU at 1280 by 720 screen resolution. And in order to do a fair comparison for both a baseline and our method, we choose one light used for shading for each primary ray with reservoir sampling. For baseline, we first select 32 light candidates uniformly from all the lights in the Shin. And then, one light is selected from the candidates using reservoir sampling. On the other hand, for our method, we choose one light for shading from the shared light list per tile using reservoir sampling. Of course, we didn't use any acceleration structure for lights, both for baseline and our method. Here is the result of our method with point lights. We did an equal time comparison with the Shin having 2560 point lights. Both images were rendered in 1 second. The baseline is shown on the left and our method is shown on the right. The image quality is evaluated with root mean squared error. Let's see the difference in more detail. This is the rendered image for baseline. And this is our method. As you can see, the noise is reduced quite a lot in our method, especially in the close-up images. Again, this is the baseline. And this is our method. Baseline, our method. Also, this is the result of our method with area lights. We did an equal sample comparison with the Shin having 2997 triangle lights. The images were rendered with 256 samples per pixel. The baseline is shown on the left, and our method is shown on the right. Also in this case, let's see more detail. This is the rendered image of a baseline. You can see a lot of noises in this image. And this is our method. As you can see, convergence of our method is much better than the baseline. Again, this is a baseline. And this is our method. Baseline, our method. Finally, limitations and future work. In this paper, we ignore the directionality of the radiant intensity for area lights for simplicity. But it can produce an additional variance. For detail, please see our supplemental document. But variance reduction for this case is our future work. And stochastic light culling does not consider the phase function on ray segments similar to equiangular sampling. So, it also can produce a variance for highly anisotropic media. Moreover, our work opens up many interesting future works. Firstly, to use our method in heterogeneous volume, we can combine our method with transmittance-based impotence sampling by multiple impotence sampling. In addition to that, we can render indirect illumination by applying our method to VPLs in participating media, where the radiant intensity of VPLs depends on the phase function. Last but not least, our method is also applicable to virtual ray lights by exchanging the relationship between the ray segment and the point light in our method. We would like to investigate these extensions in the future. In conclusion, in this work, we propose a simple but efficient method to compute single scattering in participating media. Our method extends the stochastic light culling method to volume rendering and allows us to compute the lighting in volume without any hierarchical data structure, such as a light tree. We performed experiments with the Shins containing point lights or area lights, and they show our method can obtain better convergence compared to a baseline method. And that's it for me. Thank you very much for listening.